Okay, good morning friends. So, today we will look at acoustic intensity. The concept of acoustic intensity will be studied in today's lecture. Till now we had been looking at acoustic pressure and acoustic velocity as the two fundamental quantities of interest, but now we will look at a combination of them which will turn out to be acoustic intensity. But before getting into this topic, let me go back one step and do a similar analogy with the formula that we will get in acoustic intensities. We will try to just go back one step and rederive a similar formula which is the power calculations for a spring mass system. So, we will just, this is technically not required for the acoustic calculation, but just to make a smooth entry into this subject, we will revisit the power calculations for spring mass system driven harmonically. Okay. So, the problem is the following: you have a spring of stiffness K connected with a mass M, and this is the displacement of x is the displacement of the mass. It is driven by a harmonic force which, as we know, can be qualified as f e to the power I omega t. So, the differential equation associated with this problem is well known, mx double dot plus kx is equals to f, but now since f is harmonic we might as well call it f e to the power I omega t. So, if we know for a linear system, if it is undergoing an excitation which is harmonic, the response might as well be harmonic. So, we choose small x equals to capital X e to the power I omega t, and then if we make that substitution, we will get minus m omega square plus k multiplying x is equals to f, which means capital X is equals to capital F divided by k minus m omega square. In other words, the displacement amplitude and the force amplitude is related by a constant real factor, right. So, the displacement and the force basically are in phase or out of phase depending upon whether k is greater than m omega square or k is less than m omega square. So, readily we see from this formula that displacement and force is either in phase, which happens in the low frequency zone, that is k greater than m omega square, or out of phase, which happens in the high frequency zone when k is less than m omega square. So, for high frequencies the system actually behaves like a mass, whereas for the low frequencies it actually behaves like a spring, because remember, for a spring the displacement has to be in phase with the force. If you had only the spring, kx equals to f, which means the displacement and the force had to be in phase. Now, what about the velocities? So, velocity v we know is dx dt, right. So, therefore, velocity will be I omega times x into e to the power I omega t, right, because small x has been found out as capital X times e to the power I omega t. So, therefore, capital X, if we make this substitution, we get I omega f divided by k minus m omega square e to the power I omega t. And now, I may group this I together as a phase factor, that gives me omega f divided by k minus m omega square, once again I omega t plus pi by 2. That is the factor within the exponential, within the argument of the exponential sign. So, therefore, what we have this time is the velocity amplitude is omega f by k minus m omega square, but please note that now there is a phase difference between the force and the velocity, and the phase difference happens to be pi by 2. In other words, if the force vector starts from the horizontal position, the velocity vector will have a 90-degree lead if k is greater than m omega square, and if k is less than m omega square, then it will have a 90-degree lag. So, the velocity vector will lag the force vector if there is a if the frequency is on the higher side, higher than the natural frequency. But the important point to note is that either ways there is a phase difference between velocity and force by an amount of 90-degree. So, let me write this point for you. The force and velocity phasors have a pi by 2 phase difference, which may be pi by 2 positive or pi by 2 negative, depending upon whether the frequency is high or low. Okay. So, how does the graph therefore look like? So, if we happen to plot the graph, force against time, let it be cosinusoid, what would be the graph of the velocity? The velocity graph would be either a negative sign or a positive sign, depending upon the phase. If k is greater than m omega square, it has to be a negative sign, right. So, that would be, that graph would look something like this. Please excuse my drawing, and then it will go to a peak value, and then it will come down and this way. But the important thing to note in this overlaid graph is the following, that wherever the force was going to 0, the velocity is going to its peak value. So, these peaks and the 0 values will be matching, right. So, the red one is velocity for k greater than m omega square force, that is all very fine, right. So, now if we wish to calculate the power, what is the power that is required to drive this oscillator? Okay. If you think back, the formula for power at any specific time is nice and simple, f of t into v of t, that is it, right. So, that is the instantaneous power. So, let us intuitively understand what is the power that is required to drive this oscillator from this plot. In this half, so what I will do is, here itself I will try to plot the power. In this first half of the time period, I will call this t by 4, this is t by 2, and this is again 3 t by 4, and this is t. Capital T is the time period of the oscillation, which in turn is 2 pi by omega, right. Now, what happens from 0 to t by 4? Force and velocity is having opposite sign. So, therefore, what is the power? The power is going to be negative in the first t by 4 quarter period of the time cycle. What happens in the next cycle, next quarter period between t by 4 to t by 2? Both force and velocity are negative. So, as a result, the power that will come out is going to be positive. What happens progressively in the next quarter cycle, that is from t by 2 to 3 t by 4? force is negative, but velocity is positive, as a result the power is negative. And what happens finally between 3 t by 4 and t? Both are positive. So, finally, we get to see again a positive power, and this cycle will continue. Between each consecutive quarter cycles, you will now see that the instantaneous power is going to fluctuate in sign. Sometimes it is negative and sometimes it is positive. What does the negative power and positive power imply? Negative power implies that power is actually not done by the external agent to drive this oscillator. In fact, it is the oscillator which gives back the power to the external agent, right. That is the meaning of negative power, because positive power means that is the power that is required by an external agent to drive the oscillator. So, it is only between t by 4 to t by 2 and 3 t by 4 and t that you require an external agent to actually drive this system, but whatever the power is supplied by the external agent to the oscillator during these quarter cycle periods is actually returned back by the oscillator to the external agent between 0 to t by 4 and t by 2 to 3 t by 4. This is something similar happens even in an IC engine, if you recall, that during the power stroke only the IC engine supplies power, right. In the other strokes it is actually because of the inertia of the crankshaft it is able to execute the motion, right. The power stroke alone supplies the power, but that happens to exceed the power required in the compression stroke. That is why it is able to complete the cycle all by itself, right. So, power that is required by the oscillator, let us now return back to the oscillator case, power that is required by the oscillator is actually going to be 0 in an average sense, because within certain duration it is actually the external agent which will supply the power, but in exactly the same duration of time in that is between 0 to t by 4 and 3 t by 2 to 3 t by 4, you are going to get the opposite effect, where the oscillator is going to give back the power to the external agent, and as a result it is this stage it should be obvious to you that the average power required will be 0, right. Whatever is going to the system is actually coming back, right. So, thus firstly the instantaneous power will have a periodicity this time of t by 2. If you realize it is going negative, it is going positive, it is going negative, it is going positive, right. So, this time the power, instantaneous power is not going to be of period omega, but rather it is going to be, or rather of period 2 pi by omega, but it is going to be of pi by omega. In other words, the frequency has doubled, right. So, if you look at it in a more formal sense, so we have the following expression: capital F is equals to f e to the power I omega t, and V is capital F by Z e to the power I omega t plus pi by 2, where Z is k minus m omega square divided by omega, right. So, that being the case, but f of t, what is this is in the phasor notation what we have written for force and velocity. What will be the real part of this is essentially what we are going to track. The real part of this force will be f cos omega t, and the real part of the velocity will be f by z cos omega t plus pi by 2, right, and that gives us f square by z cos omega t into cos omega t plus pi by 2, right. We can do a little more calculation by converting this as a sum of cosines. Okay. So, if we do that, you will have f square by 2 z cos of A minus B needs to be put here, which is cos of pi by 2 minus cos of 2 omega t, right, 2 omega t plus pi by 2, okay, cos of 2 omega t plus pi by 2. So, what is cos pi by 2? Cos pi by 2 is 0. So, we will have f square by 2 z into cos of 2 omega t plus pi by 2. So, you see what I told you is in fact correct, that the instantaneous power has a frequency of double the frequency of the force and velocity. This is the instantaneous power expression. So, the instantaneous power would go something like this. Okay. But what is the average value of this power? The average value of this power is readily now seen to be 0, because it is going both in the positive direction as well as in the negative direction. So, the average power equals to 0, right, because it is sinusoidally oscillating at a frequency of 2 omega between its positive extreme and negative extreme, generating identical areas below the x axis, below the t axis and above the t axis. So, therefore, the in an average sense the entire area is, if calculated within a large enough time zone, is going to be 0, right. So, therefore, we conclude that the average power required to drive the oscillator is 0, and this should be no surprise even from a physical principle, because there are no energy dissipation mechanisms that is present here. In this spring mass system there is absolutely no energy dissipation mechanism. The energy dissipation mechanisms will be in the form of a damper. Damper resembles a loss of energy. Accordingly, if you add a damper and redo this calculation, you will be now able to show that the force and displacement firstly will not always be in phase or out of phase. There will always be a little bit of phase difference between the force and displacement, which essentially means that the velocity and the force will never be allowed to have a pi by 2 phase difference. If the velocity and the force happens to have pi by 2 phase difference, then you are going to see that the power required is going to be 0. But once you put a damper, you will get you will see that this condition will never be satisfied. There is always going to be a phase difference which is different from plus or minus pi by 2, and that would essentially mean that on an average there is a certain power that will be required in order to drive the system, and that makes sense because the damper will sort of soak up the energy. It is a dissipation mechanism. So, whatever energy the damper soaks up, you need to supply that energy from the external source and thus make that oscillations happen. So, the crucial point to realize is that the cause of this power being 0 is the fact that what is important for power calculations, other than the magnitude of the force, what plays a very crucial role is the phase difference between the two quantities which actually are inherent in the power expression. Power is a quadratic term, it is a product of force and velocities. Not just the magnitude of force and not just the magnitude of velocity, what is extremely important is the phase difference between the force and velocity which rules the power calculation. So, this is where I mean this will also happen in the acoustic case. So, that is why I took a few steps backward to illustrate this for you. So, for power calculations, it is the phase difference between the force and velocity which plays a vital role. Okay. So, now we will go to the acoustic case. So, till now we have been looking at acoustic pressure and acoustic velocity. So, let us again return back to our one dimensional case to start with. So, let us say this is a duct, even if it is 3 dimensional space, no big issues, but let us start with a duct problem. So, let us say at a particular section at some x we know what is the pressure, and at present we are dealing with plane waves. So, all across this dotted line the pressure is uniform, right. That essentially means that the particles on the left of this plane are forcing the particles on the right of that plane with a value of force per unit area being the pressure. And what is the velocity at which these particles are crossing this dotted line? The acoustic particle velocity, right. So, in other words, similar to what is happening to a spring mass system, I have just replaced this mass with this dotted line, right. What was happening in the oscillator situation is that I was driving the oscillator with a force, the oscillator was moving with a certain velocity, right. And what is happening here is that on this dotted line, though it is not visible with our naked eye, there are acoustic particles sitting. Particles to the left, immediate left of this dotted line are pushing these particles which are sitting on the dotted line with a force per unit area equals to pressure, and these particles are now moving with a velocity v or ux if you may call it, right. So, as a result the same situation is happening, right. So, we could do a power flow calculation exactly in the same manner, and that leads us to the concept of acoustic intensity. So, acoustic intensity technically is defined in the following fashion. It is the power flow per unit area normal to the area chosen. Okay. So, here which is the area? The area is precisely the, this is the area, the section, right. So, what we are looking at is we are looking at the velocity of particles as they are crossing this area, right, and they are crossing this area because someone behind them is pressurizing them to cross this area, is forcing them to cross this area. So, there are two situations, that there are two quantities that are involved, force and velocity, just like we found in oscillator. Force and velocity both are involved, just that instead of force we will refer to as pressure because it is per unit area, force per unit area being pressure. So, therefore, what is the intensity going to be? The acoustic, or firstly just like we had instantaneous power expression, firstly we will define an instantaneous acoustic intensity which will be time dependent. So, the instantaneous acoustic intensity, unlike the average value cannot be time dependent, the instantaneous value has to be time dependent. It will be the power per unit area that is under investigation. For this present illustration I have chosen this unit area to be normal to the direction x, right. So, therefore, the power is going to be force per unit area into velocity in the x direction, right. So, the pressure is given by P and the velocity in the x direction is u with a subscript x t, right. So, this is the instantaneous acoustic intensity, right. Now, let us try to understand that I misspelled instantaneous. Let us try to understand the average value of this intensity as it comes. So, firstly let us take a travelling wave situation. So, for a travelling wave P t or P x comma t is going to be e to the power I omega t minus k x, and then let us refer to capital P as its amplitude. Okay. And we will call this section as x equals to 0. Okay. So, P t therefore, P at 0 comma t is going to be P e to the power I omega t. So, therefore, we are going to take the real part of it, because that is what will be our quantity of interest, right. So, the real part of acoustic pressure is going to be P cos omega t. What about u x, x comma t, that is going to be P by rho naught c e to the power I omega t minus k x, rho naught c being the characteristic impedance. So, u x at this same position is going to be P by rho naught c e to the power I omega t. So, the real part of this guy u x 0 comma t is going to be P by rho naught c cos omega t, right. So, the instantaneous intensity therefore is going to be P by P into cos omega t, P into cos omega t is the acoustic pressure, that gets multiplied with P by rho naught c into cos omega t, which is the acoustic velocity along the x direction. So, this is the intensity instantaneous intensity along x. Please remember, intensity is a vector quantity, because intensity is pressure times velocity. Depending upon the direction of velocity, the interpretation of intensity becomes vectorial. Pressure is scalar, velocity is vector. So, depending upon the choice of your direction of velocity, there is a direction attributed to the instantaneous intensity and also its time averaged counterpart. But carrying on with the simplification, what happens here is P square by rho naught c into cos square omega t, and that will lead to P square by 2 rho naught c into 2 cos square omega t, and that in turn is P square by 2 rho naught c 1 minus cosine of 2 omega t, or maybe plus 1 plus cosine of 2 omega t. So, this is the instantaneous intensity, which is varying with time as a function of time. Here what we see is that the first term P square by 2 rho naught c. So, if I just open this out, this will look like P square by 2 rho naught c plus P square by 2 rho naught c cosine of 2 omega t. The first term is a constant value, but the second term will be fluctuating between plus and minus, just like you had this fluctuation even for the oscillator, right. So, this is going to be a fluctuating term with 0 average, right. So, therefore, if you take the average value, so the time averaged intensity which we will denote with a bracket of this kind, that will be P square by 2 rho naught c. Okay. This is a very important result. Now, what we are saying that if there is a travelling wave and travelling plane wave, to be more precise, with our choice of travelling plane wave, we are actually seeing that there is a power flow happening at any arbitrary section, and that is a time averaged power flow is there, which is why we are getting this non-zero term, which is p square by 2 rho naught c. Okay. Let us look at another little more complicated example. So, what we have what we had for the case of a plane travelling wave was this, that the p by u ratio, which was the impedance, was perfectly real, rho naught c, right. But in general this is not true. You have seen examples wherein, like in the case of standing wave or even for the evanescent wave, you will see that the p and u combination or the ratio of this p by u will not be real. Just like in the oscillator case, we argued that if the ratio of p by v, the force and displacement is real, you are going to get a 0 situation for the power calculations. Similar things will happen even for the case of acoustics. So, let me illustrate to you a more general situation. So, easy in the previous problem. So, in the above problem, p by u x was equals to rho naught c was real, right, because we were dealing with a plane travelling wave situation. But if there are multiple waves coming from different directions, we know that you have a situation of standing wave, and you cannot say that the p by u is going to remain real, right. It is in general a complex quantity. So, in general p by u x will be a complex quantity, not necessarily real, right. So, this quantity will be called as impedance. This is not the characteristic impedance though. Characteristic impedance qualifies only for a single travelling wave. In general, if you wish to refer to this quantity, which is the ratio of pressure by velocity, you have to just call this as impedance. Okay. So, p by u x in general is impedance, which in general again is a complex quantity. So, what happens to our intensity calculations? Let us look at it once more. So, again we start with instantaneous intensity, which is going to be a complex pressure amplitude multiplied with e to the power I omega t. Let us for once open out this complex quantity into a real part and into an imaginary part, e to the power I omega t, right. So, I am just opening this p. I remember I told you that in general the amplitude associated with the phasor is complex, just to keep track of your phasor. So, p here is basically a certain magnitude into e to the power I phi, where phi is the phase associated with the pressure, right. But the intensity is not just p, but p multiplied with v. So, this formula as I have written it is just for p of t. So, I will do a little more manipulation with this to get at this situation, right, and that in turn leads to p r cos omega t minus p I sin omega t. That is the real part of it, and the imaginary part of it is p r sin omega t plus p I cos omega t, right. So, this is what we have in terms of phasor, but then we had taken the convention that the actual signal that will be obtained will be the real part of it, is real positive x axis at time t equals to 0. So, the real part of this pressure is going to be p r cos omega t minus p I sin omega t, right. Similarly, you could do this calculation for u x also, nothing changes basically. Similarly, for u x of t, you can do just the same calculations which p by u x. So, that will in turn lead to u x, the real part of it, into cos omega t minus u into sin omega t, right. And the instantaneous intensity will be the real pressure times the real velocity, right. So, the instantaneous intensity will be real part of pressure times real part of velocity, which in turn means P r cos omega t minus P I sin omega t into u x r cos omega t minus u x I sin omega t, right. So, let us simplify this expression a little bit in the next page. So, instantaneous intensity is going to be this expression, which I will copy and paste. Yeah. So, this is the expression for the instantaneous intensity. Let us simplify this a bit further. So, what we have is P r u x r cos square omega t plus P I u x I sin square omega t minus P r u x I cos omega t sin omega t minus P I u x r sin omega t cos omega t, right. So, in the next step we will appeal to our good old trigonometric formulas and replace these as 1 plus cos of 2 omega t plus P I u x I 1 minus cosine of 2 omega t divided by 2 minus P r u x I by 2 sine of 2 omega t minus P I u x r by 2 sine of 2 omega t. This is the instantaneous intensity. Again you get to see that the instantaneous intensity has got a frequency dependence which is 2 omega. Instead of omega dependence, you are getting a 2 omega dependence. This is actually obvious because intensity is a product of pressure and velocity. Pressure is, both of them have got an omega dependence, which is why the product has got a 2 omega dependence. But other than the fact there is a cosine of 2 omega t and the sine of 2 omega t dependence, there is also a constant term which you see here. These two terms are associated with this one value are constant, whereas these terms, all these terms are fluctuating terms, right. All these terms are oscillating terms. The average associated with these terms will be 0, or the time average associated with these terms is plain and simple 0, right. So, what is the average of this instantaneous intensity? It is going to be P r u r plus P r u x r, I am sorry, plus P I u x I divided by 2. Only the terms associated with these two ones will be responsible for the average quantity. All other terms involving the trigonometric quantities will not lead to any average value, right. So, this is what we will refer to acoustic intensity in general. When we say it is acoustic intensity, we generally mean as time averaged, as the time averaged instantaneous intensity, because that is what is physically more meaningful, because that gives us an idea that over a sufficiently long duration of time, what is the energy or what is the power that is getting transferred from the left side of that point under the consideration to the right side, right. So, whatever analysis we did for 1D is actually true for even a higher dimensional space, it is actually true for even situations which do not have plane wave, because if it even if you do not actually the plane wave assumption was only used in this formula where we said P by ux is equals to rho naught c. When we made it general, so in general, as I said, in general there will be a complex impedance. So, even if it is a spherical wave, even if it is a cut on wave, any kind of wave, even if it is an evanescent wave, any wave, with any wave you can find P and U in a particular direction, you can find the ratio of these two these two quantities. It may be real, it may be imaginary, but definitely it has to be complex, right. So, we have taken a perfectly general approach here, where we have taken that the ratio of these two quantities is complex, the quantities themselves are complex has been taken, though we could have taken one of them to be real without loss of generality, but just to be perfectly general, here what we have said is the two quantities have been taken as arbitrary complex numbers, and then we have been able to find out the time averaged instantaneous intensity, which is abbreviated as a single in a single term as acoustic intensity, and that is given by the following number. This could have been written much in a much simpler way if we said it is real part of P r plus I P I into U x r plus I U x I by 2, right. If we take the real part of the complex pressure amplitude and the complex velocity amplitude, we will end up with getting the same answer, right. With this will come with a minus sign. This will come with a minus sign. So, if you take the real part of the complex pressure amplitude and the complex conjugate of the velocity amplitude, right, then you will get exactly this same answer. You can verify that P r u x r is real, P I u x I, it comes with a minus I square, minus I square is plus 1. So, the real part of it is P r u x r plus P I u x I, right. So, this is in fact leading to this answer. So, therefore, in short form, what is often quoted in textbook as the formula for intensity is real part of the complex pressure amplitude multiplied by the complex conjugate of the complex velocity amplitude. So, star denotes complex conjugate. So, the working formula is actually pretty simple for intensities. So, the acoustic intensity working formula is simply half of real part of pressure times u x star, right. It is u x if you are interested to calculate the power flowing through an area which is normal to the x direction. If you are interested to know the power flowing through an area which is normal to the y direction, you have to replace u x with u y. If you are interested to know the power flowing through an arbitrary area which is arbitrarily aligned, then you have to find the normal to that area and find the velocity in the direction normal to that area, right. So, appropriately you need to replace that, but this is very important that we are getting half of real part of pressure times velocity conjugate as the formula for intensity, which is what you will see is often quoted in different textbooks, but usually most of the textbooks that I have come across does not give this background for the derivation of this formula, which is what we did here. So, we will take it up from here in the next class. Thank you.